Swayam Prabha. Digital India. Educated India.
So, how are you guys? So, are you enjoying here? Good? Okay, perfect. So, as said, so I am Hitash Chanda. So, I am a faculty at the Department of Physics here. So, at IIT Madras. And today I will talk about something called principle of least action or least action principle. I will not talk about anything quantum. I will talk about everything that you already know, but in a different language. Okay, and I will just give a brief introduction. There are various subtleties that we may discover in your later life, but I will not go on talk about those things. Right. So before we start on, let me ask you a few questions. So you are at the end of your class 11 and you are going to class 12, right? Perfect. So you already know mechanics, like kinematics, Newton's laws, everything. So you solve all the free body diagrams also for your JEE preparation, etc., etc. Perfect. And you have done some optics, right? For example, wave optics, ray optics. Okay, only ray optics, right? Both are there. Okay. Have you done interference? Diffraction? Not in detail. Okay. Even if you done slight hand waving manner, it will work. Fine. And in mathematics, so you have done, I think, differential calculus. Perfect. What about integral calculus? It is in some people have, because in our time, so entire integral calculus was in class 12. Okay, so I have prepared my lecture based on that. So I will assume that you know differentiation, so but you don't know integration, but we can live with that. Fine. So again, so I will talk about something called principle of least action. It will be basically a topic on mechanics, but it can be generalized to everything that we see in nature. Fine. So I will start with this question. Let's assume that you are going to a hike in some trail, let's say in Ooty or Kodaikanal, and you find two roads in front of you, right? And your guide says that both of the roads will take you to the same destination. So again, the source is same, destination is same, but the path that will take you to the destination are different, right? So which one you will choose? The shortest path, right? Okay. So some say shortest path. Anyone else want to try this game? The path that is easiest to walk, right? There is no ups and downs. Anything else? Yeah, so one that requires least effort, right? Perfect. And you will do the same if instead of two, if you have many paths between your source and destination, right? So the likely answer that either you will choose the shortest path, note on the superlative degree here, shortest, not shorter, right? Or you will take a path that will take the minimum time because you are in a hurry, or you will take a path that are least ups and downs, right? That take least effort to walk. In the opposite manner, so if you are a fitness freak, then you may try to do the opposite, that you want the longest path, or you want to take the path that takes most effort, right? And so on and so forth. But only thing that we note here that we always deal on the superlative path, either shortest or longest, depending on what you choose, right? Either you want to be fit or you want to be on time. Now I ask the same question to the nature. Okay, so let's say instead of you, so there is a photon, that is the particle of light, or even a ray of light, or a particle of mass m, let's say a ball, right? And you want, so the ball is here and it will go to somewhere in the destination, and there are many paths in between them. So which one it will choose? Sorry? It will travel in straight line? Least travel time. Okay. Anything else? Okay. Okay. So let's try that for photon. Let's consider we are the same medium. So the velocity of light is fixed So there are 2 points A and B in the same medium, and I start a light from here and it should reach B. So will they take this type of path? No, right? Why not? But these are valid paths between A and B. So there are many paths between them, actually infinite of them, but it is a non-optimal path. So what it will take is this straight line, right? But the question is why? So who programmed light to take the shortest path or straight line path between A and B? So today I will try to answer this. So basically this question, is there any deeper reason behind this shortest path that light takes in a medium from point A to point B? Okay? Okay. So again the question is, instead of U, if there is a nature, right, it can be photon, it can be a light ray, it can be a particle of mass m, which path that inanimate object will take from one point to another point. And there are infinite ways we can do that, because we can connect these 2 points in space in infinite manner. So that is our question. Fine. Why it is not working properly? Okay. So let's make the problem a bit more challenging. That what about if light travels from one medium to another medium, like a refraction? So you have done refraction, right, in high school. So the problem is now, so we have 2 medium. The light velocity here is v1, light velocity here is v2. I have point A to point B. Light has to travel from A to B. Which path it will take? It bends. So will it take this path, that path? So which one it will take, right? The main point is there are infinite paths between A and B, assuming that light travels in a straight line in a medium. Fine? So which one is the correct one? The correct one is something like that, where sine of this incident angle divided by sine of the refracted angle is exactly equal to v1 by v2, where v1 is the velocity in the upper medium and the v2 is the velocity in the lower medium. And we know this law. So what is it called? Snell's law, right? But point to be noted that, so light here follows Snell's law. It doesn't follow the shortest path. Light follows some path given by Snell's law, but not the shortest path. Fine? That's another catch. That the shortest path is not always the answer. Fine? The nature doesn't always take the shortest path. It is optimizing for something. Let's go on. Now let's talk about the entirely different regime of physics, that is mechanics, right? So we are going from ray optics to mechanics. Let's say we have a projectile of mass m, and we throw it from one point to another. And in kinematics, you all have done this exercise in, I think, second chapter of class 11, right? So the point is, you have x and y plane. So gravity works in minus y direction downstairs. You have initial point A and final point B, right? And the coordinate is x initial, y initial, and f, xf and yf. And you throw a ball from here to there with some initial velocity. Now, which path it will take? Will it take that one, or even this one? Or a bit weird one that slows down in the middle? Or even some oscillating one, right? Or even the weirder one? Which one it will take? First one, parabolic one, right? That we have solved. Actually, none of the paths are correct. The actual path is this one, where we know that the x and y evolves in time with respect to this formula. This is a kind of simple kinematics formula, right? And if you manipulate that in terms of only x and y, you throw out the t, you will get an equation for parabola, right? That we have done. And you can find this equation of motion using Newton's law. Fine? So here, so are you familiar with this symbol, d2x by dt2? So this is a double derivative of x. That means that it is an acceleration along x multiplied by m. So we get the Newton's law, right? Here m a in the x direction is 0 because there is no force acting on the x direction. Only thing that is acting on the particle is in y direction, that is gravity. So m d2 y d2y dt2 is minus mg because it is acting downwards. So this is a simple Newton's law, and by solving this differential equation, these are called differential equation, so that requires some derivative, you will get the correct path. Fine? But then the question is why? Why the particle follows Newton's law? Why not the other paths from point A to point B? Right? Who programmed the particle to follow Newton's law, or who programmed the light ray to follow Snell's law? Because if you think carefully, light or the projectile doesn't have a brain, right? It cannot think like you. So in your case, you know what to do, right? Either you take the shortest path or you take the longest path. So you know what to do, right? But light or photon doesn't care, so they cannot think, right? That means that there is a deeper reason behind this choosing this path, right? That means there is a rule book that nature has to follow. So we are talking about that rule book. So nature actually has a hidden rule book, so imprinted everything from light to projectile, doesn't matter. So, and I will tell you here that nature is basically very lazy. It does not do anything that is more than needed, right? So it is most lazy person or entity out there in the world. That's why, so it wants to minimize its effort from going from point A to point B, right? It optimizes or minimizes its effort. What that effort means, we don't know yet. We'll define the effort that nature thinks that it is my effort. We'll do that. But again, the point is that nature does not always take the shortest path. So shortest doesn't mean that it is most efficient, right? It takes some efficient path, but to define some efficiency, we need to assign some number to each path, right? For example, if you take point A to point B, right, and we have established that in principle there can be infinite number of paths that connect A to B. It can be that path or that path, or even this path, or even some kind of this kind of path, right? And to distinguish which one is most efficient, which one is not, we need to assign some number to this path. Let's say we assign some real number, by the way. So let's say we assign number 1 to this guy. Let's say here I have assigned minus pi with some consistent manner, obviously with some following some rule. Here let's say I take e to the power pi. Here I take, let's say, minus 1.234, right? So once we assign this number, this number will mean that how much a path is efficient. What we need to do is minimize that number. That's it, right? So I have many such numbers, actually infinite sets of these numbers, each correspond to particular one path, right? And then we need to minimize them. And that minimization will give us the correct path. For example, here, this path, minus pi is the lowest one, so that will be my actual path from here to there. Okay? So any question here? If you, yes?
So we still don't know why nature optimizes for its effort.
Yeah, we don't know. But it turns out to be that nature does it. So why it does, we don't know. But still, so we have figured out that nature is doing some kind of optimization and it is best at it. Yes? Yes, we will see that. Because, so depending on that number, right, how we assign the efficiency of a path by this number. This number might not be the distance between A and B or the distance of the path. If it is the distance of the path, that happens, for example, in a medium, so you throw up a light beam from one point to another point, then it will be, actually this number will be equivalent to the length of the path. In that case, the efficient path will be shortest path, but it is not always the case. As we see, for example, in case of refraction. So refraction, the shortest path is the straight line, but it follows Snell's law. Yes?
Also, in this case, like for photons especially, we say that the photon will consider all the possible paths to be before choosing the most optimized one.
Okay, why?
Yeah, that's what we can act.
So you have heard about that, right? You have heard about that? Okay, let's postpone that discussion at the end. But for now, even we measure, for example, in experiment, like you know, all know about pinhole experiment. So light in a medium, light travels in a straight line. There is no, I mean, nothing happens otherwise. And in a refraction, so it always follows Sen's law. There is no exception to that, right? Yes.
So we also, when I asked you, like, you don't know why it causes short spark, we also don't know how it does it. Like how you told us, like, how does nature think for itself?
Yeah, nature does not think, right? That's why it sets a rule book from the beginning. Let's say start of the universe. I have a rule book that I have to follow.
How is it programmed to follow?
We don't know that. But all we know that there is a rule book that it has to follow. Yes.
How do you assign numbers to paths in
That we will see. Some function, right? Some function depending on the path. So how do we assign the number? We don't know, but we have to do it consistently for each of the path. But one thing is clear that to define the efficient path, we have to assign some measure to it, right? Which measures the efficiency. That's why I am putting some real number corresponding to path, and we have to minimize it. And how do we minimize a function? Yeah, we take the derivative and set it to 0, right? And that will give us a minima. But one thing to note that at the minima, let's say this function df by dx is 0, right? What it also means? It means that the change of the function f around this minima is 0. The function doesn't change of the first order, at least in the first order, near the minima. Because df dx is basically the measure how this function changes with x, right? How fast it is changing, how slow it is changing. But at the minima, it is 0. That means the function does not change that much. So instead of calling it minima or minimum, we can also call it that at this point the function is stationary. Because it is almost not changing, at least up to the first order. Fine? Same also for maxima. At the maxima also, the derivative will be 0. So at the first order, the function is not changing. Fine? So the more common term, more general term for df dx to be 0 is called that function is stationary at some point. Fine? Okay. Now go back to our light, right? First we do what is the hidden rule that is for light, and then we will go to the hidden rule for mechanics, right? First we start with the light because it is easier. And so the hidden rule for light was given by this gentleman called Fermat. So he was before Newton's time. So I think they overlap slightly for a few years. And he was a French mathematician. And I think you all heard about him because there is a famous theorem called Fermat's last theorem. The point is he was a mathematician, right? And he wanted to find this hidden rule for light. And what he discovered that, so which we know as the Fermat's principle of least time, that light always chooses the path that takes the least time, not the least distance. So time is the key point here. Actually, for light, all this number is basically time taken by a given path. That's it. So that was his principle. So how did he find it? We don't know. But we just know that light follows this rule. That light always needs to minimize its travel time. Okay? And if we and that automatically means that lights follow straight line in a medium. If we fix the medium, the velocity is not changing, right? Then the path is always a straight line. So the least time path and the shortest path coincide. Fine? But when we do the refraction, same problem. So one thing you should note that when we fix the initial point and final point, this distance h1, this distance h2, and this distance L are fixed. Okay? Because we are fixing the point A and point B. And all the path between them is given by only this value x. So if we fix x, I can fix that path. So all the infinite paths between them are fixed by this quantity x, because this angle theta 1, let's say incident angle can be also written in terms of x and h1, right, by trigonometric formula. This angle, the refracted angle, can also be written in terms of L minus x and h2, right. So there is only one variable that can distinguish different paths. And what we need to do now? We need to minimize the travel time between all the path that is possible here, right, and then do it. So that total travel time, let's say T total is T1 plus T2, so T1 here, T2 here, right, and this will be given by L1 by V1, so L1, let's say this distance from here to this distance, right, and L2 is basically here to this distance, and divided by corresponding velocities, fine. And in terms of x, I can easily write down using trigonometric formula, Pythagoras formula, that L1 is basically x square plus h1 squared, and L2 is basically L minus x square plus h square and square root. Fine. So again, we can see that here everything is constant except for x. So if we change x, I can change my path. And what we do, I take the derivative and set it to 0. If we do that, it's a very simple calculation. It needs only trigonometry, right? You all know the formula for sine, cosine, and etc. If we do that, you will get Snell's law. So sine theta 1 by sine theta 2 is equal to v1 by v2, which is, I can write it in terms of here. So where c is the velocity of light in the vacuum, so I can write down in terms of refractive index, n2 by n1. Fine. Now, similarly, if I have many mediums, right, 1, 2, 3, 4, after one after another, then what we see that this summation, the Li by Vi, that is minimum, right, because that is the total time, and that I can write down as because c is a constant, so I can multiply this, so minimum will be remain minimum. So c by Vi multiplied by Li is minimum, and c by Vi is basically the refractive index multiplied by Li. This quantity has to be minimized for light, and that will give us the least path, sorry, the efficient path for light. So any questions? Yes. No, so the point is here. So this is for two medium, right? So this is the quantity that should be minimum. Here I am asking that there are many such mediums, one after another. Let's say a continuum of medium where the refractive index is changing, the velocity is changing. Sorry? Yeah, so because I assume that many of you might know the integration that I am always writing in some way. But yes, so this will be basically integration. So exactly. So also the when Li tends to 0, each Li tends to 0 will get an integration. So basically what we have here, so the total time is integration of refractive index n, which will depend on the length and dl. Fine. So in the continuum limit, so this summation will be this integration. But I assume that many of you might not know integration, that's why I left only with some, but they mean basically same thing. Okay, so we know now the hidden rule for light, right? Now can we have a similar rule for the projectile? The problem that we have seen, right? So what is the hidden rule for mechanics? So that is our next part. So any guesses? Sorry? Least substance, shortest path, hard path, least energy loss. No, okay. So actually the hidden rule for mechanics was first found out by this gentleman, Maupertuis. He was again a French mathematician. So he was just after the Newton, right? And he was familiar with Fermat's principle. So he found out that in case of light, this sum is minimum, right? So Ni multiplied by Li. Now for projectile, for mechanic problem, refractive index is not there. But he found out that if we replace the refractive index with momentum, then this is minimum. So that will give us the correct path. But there is one condition that we have to keep the energy fixed. So among all the paths between A and B that can have fixed energy, let's say E, And then we have to compare this quantity. So we'll assign this quantity for each of the path. Then we minimize it. And you can see that, sorry, I have to be here. If we see that if the particle takes a longer path, then this L, sum of Li is larger, right? So this quantity is anyway larger, so that is not possible. If the particle has higher momentum, right, again this quantity is larger, so that is also penalized. So in some way, we have to minimize this sum, keeping the energy fixed. So what we do, let's say we have this path, again in xy plane, this G is basically here. Now we divide this path into smaller and smaller segments, linear segments. And each of the segment, I define the average velocity V, right? So let's say Vi at ith segment, and then average length of the length of that segment Li, right? I can do the same thing for all the paths. Even for weirder path like this one, I can break it to segments, linear segments, and then I can assign at each segment some average velocity and the length. Then what I do, I calculate this sum for all of these paths, assuming that all of these paths have same energy, right? Then the principle of Maupertuis tells us that optimal path that nature follows, the correct path that nature follows, is actually where this sum is minimum, and that will give us the path between some initial point in x and y to final point in x and y. And this principle was brilliant. So at simple principle actually unifies completely different branch of physics. In one side optics and another side mechanics. Because previously, so people thought that the rule book for nature is different for different objects. But first time we are seeing that nature has only one rule book, that it needs to optimize the path, right? So there is only single principle to rule them all. Like, what is that movie called? Lord of the Rings, yes. But there is now only one principle to rule them all. Not a ring, but a principle of mechanics, light, whatever, of nature that is ruling them all now. But the problem is, so when Maupertuis first gave that principle, so he was ridiculed. So nobody among his contemporary physicists or mathematicians did not take it well enough. Because many of them did not believe it, that why this weird quantity is minimized for a path. Many of them just ridiculed him, okay, so you are just writing down from the air. And then there was another criticism is that, because remember that this is after Newton. So and the good point about Newton's laws of motion that you can get dynamics, right? You fix a time, you get the coordinate x and y at some point. But here, you just get the path. There is no time here. If you fix the initial point and the final point, you just get the path, no time. So that was one problem with Maupertuis principle, but it was a genius idea. So it gets the optimal path, but it does not tell how x and y evolves in time, like Newton's law do. Yes.
What is the thought process behind how you derive this? Because, like you said, it seems like a very random quantity to be optimized.
Exactly.
So how did Maupertuis come up with this formula that will happen?
Excellent question. Now, let me answer you by asking you another question. How you derive Newton's law? How you derive Newton's law? Exactly. So there is no derivation of Newton's law, right? Newton's law is the starting point. We don't question Newton's law. Everything follows from there. Similarly, here we figure out by lots of experiment that this quantity has to be minimized. We cannot question this. Once we believe that this is right, everything follows. So these are like axioms. So we cannot question axiom in science. We believe that these are true. Whatever follows, we do it.
But do we believe there is a deeper reason for these formulas to be there?
I think this is the deeper reason. That nature wants to minimize something that we have figured out, and which quantity it has to minimize, this is one of the quantity.
But why it wants to?
No, we don't know.
But why does it want to minimize different quantities for this?
Exactly. So the another question, the great question is, why does nature wants to minimize different quantity for different things, right? We will sort it out in the next slide. Okay? But at least one thing that we have unified, that different things about nature wants to minimize something. That is minimize the effort in a path. How we define its effort, that depends on the problem, but we will sort it out now. Okay. Now, Maupertuis was basically ridiculed during his time. So his life was basically very bad because nobody took him seriously. But there are three mathematicians, again mathematicians. So one is Euler, then Lagrange. So Euler is a Swiss mathematician. I think all heard about Euler's theorem and Euler's expression, blah blah blah, Euler's equation. E is basically the Euler's number. So that great mathematician, one of the greatest mathematician that we know until now. Then another mathematician, Lagrange. Lagrange is an Italian mathematician. And then another Irish mathematician, Hamilton. So all three mathematicians took Maupertuis seriously, right? They see a point or the genius behind Maupertuis principle. But they also figured out that Maupertuis principle had one problem, that it cannot give us the time evolution. Time is not there. Sorry? No. So what first they did was that instead of defining path between 2 points in space, where I am fixing initial point and the final point, where between them x, y, z can vary in different ways, right? Given the fixed energy, I include time in defining path. So I will start with some point in space and some point in time. I vary all the spatial coordinate and the time to reach the final coordinate. That's it. Now, to have time evolution, I will include time in defining path. Only one constant is that since we don't have time machine, so this t has to always move in the forward direction. So t can only increase, cannot decrease, because we don't have time machine. But x and y and z can decrease. So, right? Fine? So once we do that, so I can have different, let me pause it here. So I can have now different path in time in x-axis now, and y-axis I am putting the space x. So since I cannot visualize a 3-dimensional or 4-dimensional object in this animation, I will only assume that the movement is only in 1D along x-axis. Okay? And then the another axis is time. So instead of having a 3-dimensional space and 1-dimensional time, just for sake of the presentation, I am assuming that, so I have x-axis only and time axis. Okay? Now between these 2 points, so at this point I have some initial x and initial time and final x. I can now have different paths, right? Many different paths again, but now including time, not only in space. Okay? I can have very weird path even, and as you are seeing that there will be infinite number of paths between these 2 points. Again, only restriction is that the time has to move in the forward direction. So time is not decreasing, or space can decrease, but not time, because we don't have time machine. Yes. Okay. Now again, what we need to do, so just like we did before, so for each of these paths, we need to assign some number to mark it efficiency. Fine? And this number will signify whether the path is efficient or not. And this number is very weird quantity again, is not force, not time, not work done, not energy. This is something called the action. So one of the most important quantity in earth physics that you will learn when you go to college or universities, that there is something called action that will define the efficiency of a path between 2 points, that also includes time. Yes. Let's see. Okay? Let's see. I am here to tell you, don't worry. Okay. So how we define this action, right? Yeah. So just to do that, we divide this path, now here t, here x, into again smaller segments, linear segments, smaller and smaller. Smaller the segments are, smaller the better. And each segment, I am defining the average position, let's say xi at ith segment, the average position at particular segment, then average velocity vi, okay, and average time coordinate, let's say ti. Okay. I am also assuming that each of this segment takes, let's say, this very small anyway. So delta ti time to complete. So again, so x, v and t are basically average coordinate and velocity in these points, and delta t's are basically average time it takes to complete the segment. Fine? Any question here? So we are basically, we are given a path, we are making small linear segments, and each segment we are defining position, velocity, time, and also the time elapsed. 4 quantities. Right? Once we do that, so I can define another very weird quantity, but very important in physics, called Lagrangian. And what is that? So this quantity Lagrangian is a function of position, velocity, and time. And this quantity is basically the kinetic energy minus the potential energy at the ith segment. So this is not the total energy, the difference between the kinetic energy and the potential energy. Okay? Once you do that, so basically it will look like that. So this is my kinetic energy, half mv squared, minus some potential energy. I am assuming for generality that it depends also on time, but usually it depends on only position, and sometimes time also. Right? So once we define this quantity Lagrangian, we define the action of a path. That is, so at each segment, I multiply this quantity Lagrangian with the time taken, that is L multiplied by delta t, and then sum over all the segments. So this will give me a particular number for a particular path, right? And those who knows integration, you know that when I take the delta t to 0, this is basically integration from initial point in space and time to the final point in space and time. Fine? So L dt. This is my action. And one thing to note that action depends on the path. So this is kind of a function of a function. So usually if you have f of x, so what it takes a number, give you another number. For example, sine of pi, it takes the pi as input, give you a number, which is 0, right? But action is a function of a function. It takes a function, gives you a number. One second. For example, if I have 2 points, so this path, one second. So this path will be represented by some function, let's say x of t, right? If we put that here, it will give me a number. If I have another path, now path is represented by a function, so another function, let's say x prime t. If I put it there, it will give me a number. So this is a function of a function. Fine? Yes, sir.
So you mentioned that to compute action we use a Lagrangian, and we define Lagrangian for only one coordinate axis.
Yeah.
X and v x.
Yeah.
So for action, because action is supposed to be a function of all the 3 coordinate axes, and should we compute 3 separate Lagrangians?
Okay, no, action is not a function of position, time, or velocity. First of all, I'm coming. So the right question would be whether Lagrangian is a function of x, y, z or not, right? Lagrangian is a function of x, y, z, whatever you need. So there is a subtlety there, how we define Lagrangian. It has to be a function of something called generalized coordinate, where coordinate does not depend on each other. That is subtlety that I will not cover here. But Lagrangian can be function of any coordinate system, x, y, z, vx, vy, even in polar coordinate r, theta, whatever. But ultimately, here it will be kinetic energy minus potential energy. Okay? On the other hand, action, one second. On the other hand, action is not a function of position or velocity. It depends on it is a function of only initial position and initial velocity, initial position and initial time, and so on. But it is a function of another function, that is a path. It depends on the path. That's it. And once you fix the initial point and initial and final point, it can only depend on the path. And that we can write it as a function. Yes.
So what would be, so we can only define potential energy for very specific circumstances.
Mhm.
Like for example, a field. What if you can't define potential energy at whatever point you consider it?
So it turns out that, okay, there are two answers. For a mechanical problem, it turns out that we can always define a potential energy. So then you can ask that, sir, what happens when there is a friction, right? We cannot define potential energy, right? In that case, the correct answer is that you take also the source of friction into your picture, right? Then the energy is conserved. So basically, if I take this pointer, if I move it here, then its energy is not conserved. The total energy of the thing is conserved. There I can define potential energy. Okay? And since in the higher level of physics, we only interested in, let's say, atomic movement or in the planetary motion, where energy is always usually conserved most of the time. So we can work with that. Okay? But there is another answer that I will tell you about later. So that is for mechanical problem, but there are other scenarios. Okay. I will tell you about that later. Yes.
So, you already, like, this is an even weirder quantity than what nobody came up with. Right?
Yes, it is a very weird quantity, we know, but it works. That's the point. So it works.
How do you come up with that quantity? So it seems
Okay, so there are many ways to come up with this quantity. So one way, you start with the Newton's law, and after doing some calculation, you will come to this quantity. But I don't like that approach, because in my opinion, so this is much more general than Newton's law, more fundamental than Newton's law. So you start with this principle, then you find out whether Newton's law is valid or not. We'll do that here. Okay, so this comes the least action principle, or principle of least action, and it is attributed to Hamilton, although most of the work or many of the work has been done by Euler and Lagrange. And it tells us that the path taken by the particle is the path where this action S is minimum. That's it. Yes. S can also depend on mass. Yes, obviously, because there is kinetic energy, there is potential energy, right? They can depend on mass. Yes. Okay. And in mathematical notation, so we write down that delta of S is 0. Again, so just like df dx is 0 gives me minimum. So minimum of action actually written in terms of delta S equals to 0. That means that at the minimum path, the action is stationary. If we slightly change, let's say if this path is minimum, then if I slightly change the path, slightly small amount, the action is stationary. It is not changing that much. And that means that the action is minimum. Just like a function where derivative is 0. If you slightly perturb the system from that minimum position, then it doesn't change. Same logic. And that's why we write that delta of S, there is change in S is 0 at the minimum. Okay? Okay. Let's simplify this problem into only two segments. So I have only two segments, and each segment has time elapsed is delta t. So all the paths between A and B can be represented only two segments, and this x coordinate, which we call xm. If I vary xm, I can swipe out all the paths between these 2 points. Okay? Just to make our life simple. I don't want to consider infinite segments, I only consider two segments. Because if we do that, then I can write down the action as L left multiplied by delta t, L right multiplied by delta t. So L left is basically the average initial position, the x initial plus xm by 2, and average velocity xm minus x in by delta t. So position, average velocity multiplied by delta t, and same for the right. Then the least action principle actually boils down to taking that derivative of s with respect to this coordinate xm to 0. Right? Simple. If we do that, again it is not very hard calculation, I will not follow it, you can do it in your home. What you will find out that it will give us some equation called, again, very important equation, one of the most important equations in physics is called the Euler-Lagrange equation. Here, let me note you down that if you don't understand this quantity, with respect of d, I give a del here, so it is called partial derivative, and it tells us that when you take the derivative, you assume that all the other quantities, all the other variables are constant. So here, for example, when you take partial derivative of L with respect to x, you assume that you assume that v and t are constant. and similarly for here. So here again, so this is basically partial derivative of L with respect to x. Then here, partial derivative of L with respect to v, the velocity, and then you take the total derivative of time and take the difference, set it to 0. So this equation you will get by minimizing the action from the least action principle. So this is the consequence of least action principle. I think I'm almost time. Anyway, but I will take, I think I can take 10 more minutes. 10 more minutes? 5 minutes? Okay. I think Raghubir is anyway here and he takes 2 hours. So. Okay. So, again, so Lagrangian is basically kinetic energy minus potential energy, right? I can write it down that half mv square minus ux. For simplicity, I can assume that ux doesn't depend on time. Okay? And if I do this derivative, I get minus del u del x, which is basically force that we know, right, from our high school, right? And then the second quantity, I can first I take the inner position, so inner the term within the bracket, I get mv, and if I take its again time derivative, I get ma. That means the Euler-Lagrange equation gives me f minus ma equals to 0 or f equals to ma. What is that? Newton's second law, right? So, again, starting from the least action principle, I can get the Newton's law. So, in principle, it is much more general than Newton's law. Yes, sir. We are not assuming. So, that is what partial derivative means. In principle, will depend on position, but basically what we are assuming for now that velocity and position are independent quantity. So I can take partial derivative, not a full derivative. The full derivative with respect to x, the standard derivative that you know, will have a velocity component. But since we are defining partial derivative, we are using partial derivative, so we are assuming that when we differentiate with respect to x, we keep v constant and vice versa.
Suppose we were able to express potential energy at a given point and also velocity.
Yeah, so then also this term, there will be some u. So I am not assuming that usually potential energy doesn't depend on the velocity. If it does depend, then again, so this equation will remain valid. Okay, this equation will remain valid. But from this consideration, we get the Newton's law. Okay, and if you do that same thing for projectile problem, and again, so you get the solution for the projectile. Okay, I think I will move on. Now the question is, if the least action principle or the Euler-Lagrange equation be the same thing as the Newton's law, why do we study it? Why do we consider it? First thing, why do we consider it? That it will make our life simple. Because when you do Newton's law, you know that you have to take these free body diagrams in a very weird way, right? And it can make our life very complicated. But here, writing down the Lagrangian only takes to note down two energies, kinetic energy and potential energy. For example, in case of chaotic system, I think Professor Arul will teach you about that. I take inverted double pendulum in a very small, the difference in the initial condition is very same. And then if we let it evolve, let's see. Yeah. You have a lecture on chaos. Anyway, so there he will show you. So look that initially, so these two pendulum have exactly same motion because they are very close to each other. Their closeness is 10 to the power minus 5. Even they are now same, but now they will be different. So in the chaotic system, we cannot predict their motion for indefinite time. And in that case, to solve this system, doing in the Newton's laws of motion way is very problematic. Because the second pendulum is in a non-inertial frame. And non-inertial rotating frame, where the velocity of rotation depends on the first pendulum. It's a very complicated problem. You cannot do it in a simple free body diagram way. But if you do the Lagrangian way, it is simple. At least you can get the equation of motion. Then using a computer, you can integrate them out. That is one reason that it makes our life much simpler. That's why we consider this least action principle. We just need to calculate energies. But there is one subtlety that the coordinate system is a problematic part. But I will not talk about that later. So when you go to colleges, you will learn about that. Okay. There is another reason. So that was told by this lady, another mathematician, Amy Noether, right? So she tells us that, so if we are using the Lagrangian mechanics or least action principle, we can understand why there are some conserved quantities in nature. Why sometimes momentum, angular momentum, even energy is conserved. And it turns out that, so they are related to the symmetry of the problem. If the Lagrangian is symmetric in some certain fashion, we get conservation law. So for example, if we take the projectile problem, so this is my Lagrangian in that case, right? And you can see that this does not depend on x coordinate. So the Lagrangian at position x is exactly same as if I do some translation here. So this problem has a translation symmetry along x. Automatically, it boils down that there is a conservation of momentum along x direction. On the other hand, in the y direction, so this depend on y. So if I translate y axis, this is no longer same. There is no translation symmetry along y. Sorry, this will be y. The momentum along y is not conserved. And even energy is conserved because this is a translation symmetry in time. So symmetry in time, translation symmetry in time also tells us that energy is conserved. That is one reason that we should consider Lagrangian mechanics, because it gives much more better information than Newton's laws of motion. And most importantly, that this is even more general than Newton's law. And it unifies almost all the physical laws in a single equation. That is, this delta S equals to 0. This is the closest we have been to the theory of everything. So we find out the action, we minimize it, we get the path, we get the correct solution. So this equation is the theory of everything that we know of. But then you can ask that once again. So from principle of least action, we get the Lagrange equation, and if I put the Lagrangian as kinetic energy minus potential energy, we got Newton's law, right? But then why this is much more general than Newton's law? They are equivalent. If one is more general, then other is also needs to be more general, right? Because we just show that if I take this, then they are equivalent, right? Why I am telling you that this is more general? What is the answer? Sorry? Exactly. So it can be applied to beyond where Newton's laws are not applicable. Only thing is that, so this definition of Lagrangian, that is kinetic energy minus potential energy, is only applicable where Newton's laws are valid. In other words, in other cases, we have to modify the definition of Lagrangian. That's it. But all the other things still holds. Okay? A simple example will be, let's say, a charged particle moving in a uniform magnetic field. In that case, we know the kinetic energy, but there is no potential energy because magnetic field doesn't work, right? The particle always travels perpendicular to the, exactly. But then, if we believe that this is a correct Lagrangian, we don't know how we get there, but this is not the potential, but we just put it there for some weird reason. If we then solve this type of equation, we get the correct force equation. I think you know, right, this equation. This is called the Lorentz force. I think in class 12 we will see that. But starting from this Lagrangian, you can get the Lorentz force law. But the question is, then why, how do we know what is the actual Lagrangian for a system? The answer is we don't know. There is no way that we can do it. The only way we can get the Lagrangian for a system is a guesswork. It's a pure guesswork, but an intelligent guesswork. For an unknown system, given unknown system, the only way to get the Lagrangian of the unknown system is pure guesswork. But that guesswork is based on experience, years of experience on similar system. So we know the Lagrangian for one system, and this is very similar to the other system that we are studying. So I can just tweak it a bit. Let's see whether this works or not. Then comes symmetries of the problem. So we know that, okay, this system has translucent symmetry. That means Lagrangian also has to have translucent symmetry, and so on. And finally, the most important is experimental input. We want to have a Lagrangian or least action principle where the final equation of motion must match with the experimental result. And that's why there are lots of trial and error. And after that, So even I think you all know heard about standard model of particle physics, and that is defined by this long Lagrangian. And everything that is happening in this room, except for gravity, is given in this equation. It's very complicated because those are not numbers or functions, these are matrices, these are something called tensors and complicated thing. But years of experience and years of trial and error gave us this Lagrangian. And my final answer, my final one will be that when I'm calling that the Lagrangian mechanics will always give us the minimum path, that is where action is minimum, it is not true. Sometimes we get also saddle point because we are only taking the first derivative. So I can have a saddle point here where in one side this is maximum, on another side is minimum. So those are also technically the valid path. And when we do the least action principle, so what we get usually is that not the minimum but sometimes also a saddle point. Usually never a maximum. So that's why the more general term will be the principle of stationary action. Because the action is stationary, that is much more deeper doing, not the minimum one. Okay? And final slide is that.
So theoretically, we were able to have multiple different paths.
Yes.
Going to stationary action. All of them will be equally viable.
Yes.
So then it's a random as to what.
Sorry?
It's like random as to what the particle.
Sorry, I'm not getting you.
If we have multiple paths where the action is stationary,
Mm-hmm.
then it's random as to which.
No, it is not random. So it depends on the initial condition. So depends on how close you are to which path.
What is it? Equally viable.
Yeah.
It chooses one of the paths, right? So depend on, because usually theoretically we can have such contract problem, but usually one chooses one of the path. Okay, and usually what happens that we get only unique path. Okay. Anyway, now the final point is that if there are infinite number of paths, but nature is always taking one path, what about all the other paths? Are they useless? Are they useless? Actually, it turns out that it is not. And it was first shown by this gentleman, the only physicist in my lecture, Richard Feynman. All the others are mathematicians that I have shown. I am a physics teacher, by the way. So only physicist in my lecture. So he said that all the paths are equally important, right? Because if we decrease the particle size smaller and smaller, the quantum mechanics takes over and the nature becomes very weird. And it turns out that it is so weird that the electron, a quantum particle, very small quantum particle, or a photon actually takes all the path all at once. How it does, we don't know. I mean, we don't properly understand quantum mechanics yet. I mean, we know how it works. We know all the formulas and all the rules, but actually what is going on, we don't know. But it turns out that if we follow the formulation of Feynman, we can see that the electrons or photons goes through all the paths all at once. But just like light, where light interferes with each other, these paths will also interfere with each other, sometimes constructively, sometimes destructively, and at the end, if you add up something, you get the correct path. That is a path of stationary action. But not far from here, so this experiment was done in Bangalore, right, where it is basically a three-slit interference experiment. Like if we take the classical path, it's a green one from this point to that point, and then there are non-classical paths that are equally valid by Feynman. So, for example, the light comes from slit A, again goes back, very weird, goes back to slit B, and then again comes out from slit C. So, in this experiment, they confirm that these all paths also exist, and light actually takes those paths also, equally probably viable. But that will be a course on quantum mechanics, but I will not talk about that. So, that will be a story for another day. Yeah.
So is that weird path also a path where action is stationary?
No.
It's not.
Action is stationary only along this green path.
Okay, so that's the most preferred path. But light also travels.
Actually, so according to Feynman, all the paths are equally valid, right? But when you take the sum of this path, with some interference pattern, you will see that the most probable path is actually the classical path.
Most probable, but other paths are also.
Yeah. Most probable once you take care of all the interference from all the other paths, because many of the paths will get cancel each other because they will most of the paths will cancel each other because they will destructively interfere. Only thing that will remain at the end.
Cancel each other, does that mean the photon will never take that path or?
Okay. Actually, photon does take the path. The only thing what we will see the most probable path. But there is also another experiment that you can do. Actually, in this experiment they do. So they actually block the other paths so that some paths do not destructively interfere. That's why they detect this third path. Right? So you have to block certain paths so that they are not able to do destructive interference with other paths. Then you will see non-classical path. So I think, yeah, in YouTube you have seen some videos, right? In veritasium, so you have put a diffraction grating, you see another, yeah, perfect. But this will be story for another time. I think, anyway, Professor Raghuvir is waiting for some time. Thank you. So, any questions?
Swayam Prabha. Digital India. Educated India.